So we continue with matrices in R. So last time we looked at matrices and how to add them, how to find the inverse of a matrix, and how to perform matrix multiplication. We ended with R bind in R. Now we can move on to C bind, which stands for column bind. To create a 3 by 3 matrix. So C bind, the first row, I could write it as 1, 2, minus 1. The second row, 1, 2, and 1. And the third row is 2, 1, and 1. Print A. And there is our matrix. So we can do something called slicing in R. Slicing is pretty common in most programming languages when dealing with matrices. So slicing helps us to pick out specific columns or rows from a matrix. Suppose we want to pick up the first row in the matrix, so I would like to print A, but only the first row, so open square bracket, close square bracket, 1 comma colon. So that would select the first row and all columns in the first row. Sorry, no column there. Colon is used in MATLAB. So what we have here is 1, 1 and 2, which is the first row. In a similar manner, we can pick the first column or the second column by switching the index. So comma 2 instead of 1 comma, we'd end up getting the first column. You have to realize that R doesn't make a distinction between a row vector and a column vector. In either case, it is going to provide you with a list. So let's see if it is a matrix. So I am going to create a temporary variable y, and that would be the second row of the matrix. And I would like to see if it is a matrix, so I'm going to type is.matrix. So is functions and as functions are common in R. So we have is.matrix, as.matrix, is.list, as.list, and so forth. So is.matrix y, I'll call that test.y. Print test.y, and as I mentioned, we get a false. So by default, R doesn't return a matrix even though we sliced from a matrix. So what we have to do now is take y and define it as dot matrix of y, and this time when I print, I will get a column vector right here, which is 2, 2, 1. And now, even though we wanted a row vector 2, 2, 1 in the matrix, it returned a column vector. So by default, all vectors are column vectors in R. So in a similar manner, we can select multiple rows and columns. For instance, I could create a temporary matrix H, and I would like to select the first two rows, so 1 column 2 comma. So this would simply imply that I'm picking the first two rows of the matrix A. And that's what I get here. So notice if we slice multiple rows and multiple columns, whatever R returns is a matrix. However, if we simply slice one row, one column, then it would be returned as a list. Let's try this for columns. I am going to pick columns 1, 2 to 3. And I have columns 2 and 3 selected. Now one may want to select arbitrary, not arbitrary, rather columns or rows that are not in sequence. In the sense, if we look at H, I went for 1 to 2, and here 2 to 3, and it's a formal sequence in succession. But what if I wanted to pick columns 1 and 3 instead? So if we have to do that, we will simply say C 2, 3. So this part right here selects the second column and the third column from the matrix A. And that would give us the second and the third column, but what I wanted is 1 and the third, or the first and the third, so that would be the first column and the third column. We can also get the dimension of a matrix. The dimension of a matrix is simply given by dim of, say, C, and it is going to return two elements or a two-element list. And oh, I did not save a matrix C. So you can see that I have 3 and 3, indicating that there are 3 rows and 3 columns. So we can access individual elements of the dimension by calling D of 1. That would give you the row dimension, and D square bracket 2, it'll give you the column dimension. We can find the transpose of a matrix easily. The transpose of the matrix A, I'll call it B, is simply T of A. So print A and print B. and you will see A is 1, 1, 2, and here we have the transpose of the matrix A, which is the matrix B. And one of the things that, one of the utility functions that is most commonly used in R is the apply function. So what does the apply function do? Let's take the matrix B, and let's say we want to sum across all the columns for any given row. So I'm going to specify 1, which indicates the margin right here. So 1 is for the row margin and 2 is for the column margin, and the next argument is fun. Fun is sum function, so I'm going to specify sum. So it's a standard function, so I'll specify sum, and I'll save that to a variable w, and that is the corresponding sum. So in this case, I have the matrix B, and I am summing over the first column. I end up getting 1 plus 1 plus 2, which is, excuse me, I'm summing along the first row. 2 plus 1 is 3, 3 minus 1, 2. And the second row, I have 1 plus 2 plus 1, I get 4. Third row, I get 2 plus 1 plus 1, I get 4. What if we have to do it along the columns? In other words, let's just say we want to sum the values across rows for a given column. So all I have to do is change the margin from 1 to 2, and this time when I print, I get 4, 5, 1. The matrix B is 1, 1, 2. If you add all the elements for the first column, then we have 4. The second column, 2 plus 2 plus 1, we'd have 5. And the last one, 2 minus 1, I get positive 1. So could we use a user-defined function, something that we created, so let's define a function mat.fun. And mat.fun is going to take in a matrix A, and it is going to look at, for instance, the margin, which could be a column or row. Let's say we want to go across the rows of a matrix. To access elements of a matrix, we can either go with our standard slicing operation here, or more commonly we could use a for loop. So for I in 1 to A, sorry, D of 2, D is the dimension of A. So I want to go across all columns, and this is what I'd like to do. I want to create a vector named t of I. I'll define t to be 0, we have to initialize. And I am going to take each value in the first column multiplied by 2. The second column, I'm going to multiply it by negative 1. And the third column, I'm going to multiply it by 2. And that sum is saved to vector t. And let's return t. And that is our function. So if we simply did mat.fun of a, it is returning nothing. So we end up getting 5, 4, and negative 1. So the first row, I have 1, 1, and 2. 2 times 1 is 2. Negative 1 times 1 is negative 1. If we add those two, we have 1. And 2 times 2 is 4, and 4 plus 1 is 5. So, as expected, for a given row, it is picking up all columns here, and it provides us with the sum as we have defined up there. Now, one may say, well, could I apply the apply function with matfun? It is feasible, but we have to make a bit of change. So mat dot fun dot apply, creating a new function. I'm going to pass in a, and I am going to simply do for the sum of a minus prod of a. Prod stands for product, and if I did that, mat.fun.apply could take in a matrix and we end up getting 18. So does that make any sense? So we have the sum of a, which is 1 plus 1, 2, and 4, minus the product of a. It's 1 times 1 times 2, which is 2, and that is nowhere close to 18. So let us try to sum all the elements of the matrix A, which is 10, product of all the elements of A, which is negative 8. So when I subtract 10 minus of minus 8, I get 10 plus 8, it returns 18. But that is not what we want. If we want to use it with the apply function, we want to specify it with respect to rows and columns. So this time I'm going to do apply matrix A, column, along the rows, and I'm going to use my custom function and see if this works. And we end up getting 2, 1, and 2. Let's see if that makes sense. So what it's doing, it's going for the first row. The sum of all the elements is 4, 2 plus 1 plus 1 is 4. The product of the elements would simply be 2, and if we subtract 4 minus 2 is 2. The second row, 2 plus 2 plus 1 is 5, and the product of those would be 4, and 5 minus 4 is 1. The third row, we have 1 times 1, 1 plus 1 minus 1, which is 1, minus the product of those, which would be minus 1, and 1 minus of minus 1 would be 2. So we can see a key difference between using the apply function and using mat.fun.apply on a matrix. So when we first applied it directly to the matrix, it simply printed the sum of A minus the product of A. In other words, it took all the elements, found its sum, found its product. We ended up getting 18. However, if we use it with the apply function, we have apply a, 1 mat.fun.apply. What it's doing is it's going to take the first row of the matrix A, and it is going to pick the row because we have specified the margin as 1. So to take the first row of A, apply the function mat.fun.apply, give the value 2, pick the second row of A and use the function mat.fun.apply and give the value 1, and lastly it'll take the third row and give the value 2. If we changed it to apply a, 2, mat.fun.apply, what had happened with the rows is now going to happen with respect to the columns, and so it's going to take the first column, the sum of the values is 2, the product is -2, and 2 minus -2 would be 4. The sum of the elements in column 2 is 4, the product is 2, and 4 minus 2 is 2. The sum of the columns elements in column 3 is 4, the product is 2, and 4 minus 2 is 2. So the apply function can be used with a predefined function as well as a user-defined function such as mat.fun.apply, but we do have to be careful that the input argument is a matrix and understand that the apply function is going to deal with a matrix depending on what margin we specify. So margin 1 indicates rows, margin 2 would indicate columns. Suppose we have a linear system, and let's say the equations are 3x minus y minus z equals 4, x plus y equals 9, and 4x minus y plus z equals 12. It's x plus y equals 9. So the first thing to do would be to convert the system to a matrix. So I'll define the matrix as A, and we have to put the coefficients. So we know how to define a matrix. It's simply the matrix function and specify the values inside as or using a list. So the first equation has 3 minus 1 minus 1. So 3 minus 1 and minus 1. The second equation has 1, 1, and z is 0, so 1, 1, 0. And the third is 4 minus 1 and 1. So that would take care of the left-hand side of the matrix, of the linear system. The right-hand side is simply the values on the right hand side. So 4, 9 and 12. And we'd like to solve the system, so solve A, comma, B. And it is giving us an error, and it says that A must be square, and there are multiple things that we have to address in the sense that we have not specified the dimension of the matrix. So we have to clearly specify the dimension of the matrix. So we'll define n row equals 3, n column equals 3, and by row equals 2. Oh, I'm sorry, true. And combine all the coefficients and put it as a single list. And that matrix is 3 minus 1 minus 1, which is the which gives us the coefficients. The left-hand side of the first equation, 1, 1, 0 would be the coefficients of the left-hand side in the second equation, and 4 minus 1 minus 1 would be the coefficients on the left-hand side of the third equation. And B is the right-hand side. So we have A and B. We can go ahead and solve. We don't have to worry about B, even though I have specified here B as a matrix with just 3 elements, and as I said, R is going to treat any matrix as a column vector in general, which is why 4, 9 and 12 is defined as a column vector. So I could specify the number of rows is 3, number of columns equals 1. It is always good practice to do that. So and we get that. So we have the roots 3.77 and 5, the solutions 3.77, 5.22 and 2.11. Just like maxima, R can help us find eigenvalues and eigenvectors. We don't have to load a specific package. Eigenvectors and eigenvalues are default in the base package of R. We'll simply say eigen A. and that's what we get. You can see that we end up getting a list for this eigen decomposition. So the first one here says that those are the values, and here we have the vectors. So if we want simply the eigenvalues, we could say eigen, I'm sorry, v dollar values, save that to eigenvalues, and eigen dot vectors, I'll save v dollar vectors to eigen dot vectors. So when we perform eigenvalue decomposition in R, it is going to return a list where the first element of the list contains the eigenvalues, the second element of the list contains the vectors, and it is a named list, and which is why we are using dollar signs. But would it be any different if we used the indices of the list? No, we could do that. I'm going to say v bracket bracket 1 and eigen dot vec 2. So let's type and see what eigenvalues has. That's what we get. And eigenvec would be the same as eigenvectors. And eigenval would be the same as eigenvalues. Typically, if you have a named list, it is better to simply go with the named list that we have and use the names in the list to access the elements returned by some function. In Maxima, we had the flexibility of normalizing using unit vector function, but in there are additional packages which can give us a unit vector. I'm not sure if the base package does it, but we can write our custom function to give us unit eigenvectors. So I will call it unitize. It's the name of my function. It is going to take in a matrix, and let's make use of the apply function also. So what should unitize do? It is going to take each column vector, find its norm, and divide it by the value of the norm. So how do we find it? So the eigenvectors, the first one, if we have to access, we will have eigenvectors 1, and with an apply function, by default each column is going to be passed here. So what is the dot product? Simply the eigenvector or a vector and its product. So we could do T transpose of T, that is actually doing the outer product. So t times t, we end up getting that. Let's see. Okay, so and we have to sum these values, and since we have complex numbers, we have to take the magnitude and divide it by divide the vector. So what we can do here is define sum and a. We're going to use the logic that we used with mat.fun.apply. So we passed the matrix in, we did sum a minus product a. So here we're going to pass the function, pass the matrix in. First we're going to find the product of the two vectors. Again, when you pass in a matrix A to a function, it is going to get passed as a matrix. But I'm going to use the unitize function with an apply function, where when a matrix is passed to the unitize function, it is either going to take the rows or the columns. So depending on what margin we specify. So I have P defined as A times A, and I need to square each of the elements. So if I did T squared, I end up getting that back. Now, if we did abs of P, T, we end up getting that value. Since the numbers are complex here, if we want to get the magnitude of each of those complex numbers, we can make use of the abs function. But if we use the abs function for a real number, get 9 and negative 9 would be positive 9. So with a real number, the abs function simply returns the absolute value of the function, whereas for a complex number, it would return the magnitude of the number that we passed. So we can't use p squared, we should rather use abs of p, which would take all the magnitudes. So step by step, first we are going to pick a column of a matrix, then we're going to apply the t multiplied by t, or simply we could do the abs function, and we get 3, 1 and 4, and we have to sum all the values and take the square root, and we get that. So let's see if it sums to perhaps it's best I do this with real numbers. Let's just create a new matrix. I'll define a new matrix. I'll call it B matrix 1, 1, 2, 2 or 3, 1, 1, 0, 0, 1, and row equals 3 and column equals 3. And the matrix B would end up being this: 1, 3, 0, 1, 1, 0, and 2, 1, 1. Keep in mind, by default, R is going to take the values of the list and put it in columns, column by column. So 1, 1, 2 goes in the first column, 3, 1, 1, next column, 0, 0, 1, in the next column. So if I took the first column, it is 1, 1, 2, and I'd have to find the dot product of that, and I will get 1, 1, 4, and I have to sum these values and divide each of them by the square root of 6. So let me explain what I'm doing here. Just bear with me for 1 second. So we have our matrix, which is B, and the first thing to do is to pick a column, and we have 1, 1, 2, and the next step is to find the dot product, and keep in mind that this is a vector, and this vector is defined as a column vector. So what I'm going to do is I'm going to take the transpose times B, and that's giving me 6. In other words, the dot product of 1, 1, 2 with itself is 6. So the norm here is 6. So what I'm going to do is I'm going to normalize this by taking the vector B divided by the square root of 6, and I'm going to save it to some value x. So now x is a normalized vector. So if we take x and find its dot product with itself, we will get 1. So we have successfully normalized it. So we have to take these steps and use it in here in the unitized function. So what I'm going to do is I plan to use the unitized function with the apply function, which means the apply function by default is going to pass rows or columns one at a time. So I am going to do the same thing that I did over here, knowing the fact that I'm going to get either a row by row of either row by row of matrix of a matrix, or a column by column of a matrix. So I am going to take in the value that is coming into the function from the matrix, from the unitized function. So I'll call that to be vector or vec, and that will be A. So I plan to use unitize with the apply function, which is why I'm defining it this way. So now that I have A saved to vec, because A is going to be a vector, I'm going to find the dot product, which is the transpose of the vector multiplied by vector. So vector is a column vector, transpose of that column vector here, vec variable is row, which would give us the dot product. Now we have to divide the original vector, which is stored in VEC, by the square root of the dot product, and we can return VEC. Let's run this function, and before we proceed with execution, recall that for the first column of the matrix B, the normalized vector was that. So we would end up getting so this must be something recently implemented in R. We're getting an error that in vector over square root of dp, recycling array of length 1 in vector array arithmetic is deprecated. We have to use C or as vector instead. So just like the as matrix part, I'm just going to wrap the vec object by as.matrix and run this again, and the error has to go away, hopefully. Should have said as.vector to run unitize again. Still there. Strange. Okay, but it's just a warning, it's not an error, so we can proceed as is. Perhaps we could try with C and see what happens. Same error or warning. Could be from DP. Let's try that, convert it to a list as well. And it went away. So the issue was DP wasn't a vector, it was a scalar, so we just have to convert it to a vector, and that's what I did over here, and then the warning went away. So now I'm going to try and use the unitize function that we created with our matrix and see what happens. So apply matrix B, and I'm going to take each column and apply the unitize function. Save that to W. And that's what we get for W. So it took the original matrix B and we ended up getting that. So B, this vector right here, did not have unit norm, and that W are the normalized vectors. Now we could also do the same for the rows, normalize it with respect to the rows by saying apply B, comma 1, comma unitize. Let's save it to U. And that should give us row vectors that are normalized with respect to row norm. So what we did here today is looked at matrices and the utility functions that we can use in R with matrices, and one of the most commonly used utility function is apply. And key thing to notice here is when we pass a matrix to apply, it is going to take each row or each column and apply whatever function that we specify in the third argument. If we specify 1, it is going to take in each row, and if we specify 2, it would take in columns.